Now I want to explain another article which is similar. I mean, it is RNN, we are using stack, but it's a little bit different. And I want to focus on this important. By the way, Thomas Mikolov, if I'm not wrong, is the same person who was working on word2vec. He has written many articles on word2vec, if I'm not wrong. And so this is an important article. Sometimes our RNN has lots of problems because it cannot even work for an algorithmic patterns. If you love computation theory, those computability, reachability, and those ideas in classical computation, classical computer science, let's say, those push-down automation, those finite state machines, those formal language theory, context-free grammar, and those important things. If you want to work on those things, your traditional RNN is not enough. You need to know more about push-down automation. Because, as I said, DNA in your body, there is a field called DNA computing. It's like a push-down automation plus a recurrent neural networks, because it's like a machine. So let's focus on this article. So we have a sequence generator, and we wish to learn these complex things. It could be an infinite tape, and we want to learn that. We find that these regularities are difficult to learn, even for some advanced deep learning methods. Forget deep learning methods. It's very naive in comparison to what our DNA inside our body is doing. And so if you draw inspiration from DNA, and also if you draw inspiration from neuroscience, computational neuroscience, you will have many good algorithms, much better than deep learning methods. And we attempt to increase the learning capabilities of recurrent nets by allowing them to learn how to control an infinite structured memory. We explore two basic topologies of this structured memory: push-down stack and a list. So this is a simple recurrent neural network. You know, these are states, the previous hidden state, and now it is updated like this. And if you know the hidden state at any time step, you know the output at any time step. Everybody knows these things. So let's review what is a stack vector at time t. You push on the stack and you pop, you know. So the first one, which is the top of the stack, we say that st of 0. So st of 0, this becomes f sub t of 1, and you know the rest. So push-down network uses similar idea. So instead of just saying we just say that what is the probability of a push action. So we also have this probability of push action. What is the probability of push action? And you know, 1 minus what is the probability of push action is what is the probability of pop action. But some people have 3 different actions: push, pop, and nothing, do nothing. But let's focus on this simple scenario that we only have push and pop, nothing else. And now your action is a combination of a linear matrix, but F is the nonlinearity. And now your push-down network is updated like this. You use hidden state, but also you use your previous stack vector and the second entry of that. So this becomes the first entry of that. So this is how it is updated. But in general, this is your law. This is the law. And here, I mean, the K topmost element. So until here is your traditional recurrent neural networks that you are proud of. But if you just add the stack, you will see how important it becomes. And adding the no operation, as I said, you can have push, pop, and no operation. allows the stack to keep the same value on top by a minor change of the stack updates equation. So until here, it's everything, you know everything. But now we add another term, which is no operation action. And using the top stack. But at time t minus 1, time minus 1. And here we update it for time t. And double linked list. This reminds me double strands in DNA that you separate, and it's a complex process. But here is very simple. You just update, given a list, so L is a list, given a list and a fixed head position, head, the updates of your list are like this. And here they have compared, for example, for layering different structures, they have compared. You see, LSTM is a little bit better than, RNN. But this is the least RNN that gets 100%. But we still have the problem in this pattern. So stack RNN is what you need because it works well, the good accuracy for everything. But it is not enough because this is a little bit harder pattern. So you need stack RNN plus rounding and 40 plus 10. And so what is the optimization you use? You cannot just use SGD, stochastic gradient descent. You need some search mechanism to improve it. And this is how it looks like. So stack a top, it looks like you have a couple of actions, pop action and then push action and then pop push action. And what I love about the application is language modeling. Because, transformer architecture has huge computational complexity, but nobody talks about that. But in computer science, the most important thing is computational complexity, the efficiency of your algorithm. Otherwise, everybody can draw a new algorithm every day, every minute. But the important thing is your computational complexity. And there are, for language modeling, as you have seen my playlist for language modeling, we have perplexity. So for validation, they have this perplexity. For test, we have a different perplexity. And they have compared for stack RNN, your traditional RNN, LSTM, and they have seen the results.